All right, guys, we're going to get into quadratic functions, talking about how to find their equation and some properties of them and whatnot. So let's jump right into it. So again, we're going to analyze graphs, write quadratic functions in standard form, and use the results to sketch the graph, which will tie back into all the things we've done with transformations before. And then we will find minimum and maximum values in real-life applications. Alright, so first off the graph, here's some basic characteristics, like some of the stuff we talked about earlier in the year, just about the basics of a quadratic. So again, the domain's going to be all real numbers. These things go on forever and ever, no holes, no asymptotes. This right here is just for the basic parent function y equals x squared, because things will change once you start transforming them. But the basic one, of course, has a minimum at 0, 0, so that makes the range be 0 to infinity. Including 0, and definitely has an x-intercept at 0, 0. We can see the function is decreasing, right, as we're coming here. It's decreasing from x value of negative infinity until you get to 0, and then at 0 it hits minimum, and then it starts to increase. Okay, so that's the decreasing and increasing. It's an even function, something we may not have talked about too much, but basically even functions are just symmetric about the y-axis, meaning that the y value, for example, at 1 is the same as the y value at negative 1. And the y value at 2 is equal to the y value at negative 2, that kind of thing. It's just an axis of symmetry of the y-axis, which is x equals 0. Okay, and we see the other one on the right-hand side of the screen. Same thing, this is just with a negative a value. This would be like y equals negative x squared. And it has a lot of the same properties. Of course, the range changes because it has a maximum now instead of a minimum, but a lot of the same other concepts and properties hold. All right, so of course we know things can be changed and transformations can happen. Graphs can be shifted, stretched, reflected, all that good stuff. So let's look at a couple examples. Let's see if we can sketch the graph by hand and then compare it to the parent function. So first off, part A here, we have g of x equals negative x squared plus 1. Okay, so let's think about what might be happening there. So I see two transformations. I do see a plus 1 on the outside, and then there's of course a negative in front of the x squared. So the plus 1 on the outside is going to shift the vertex up 1 unit, and then the negativeness on the outside is going to reflect the graph downward. Okay, so this graph would have a vertical shift as well as a reflection in the over the x-axis. Okay, while part B has a couple things going on as well. This one, I can see again that there's a plus 2 inside the function. It's part of the thing getting squared, and then a minus 3 on the outside. So again, the plus 2 inside is going to shift your vertex 2 units to the left. Remember, it's inside, it's the inverse direction. And the minus 3 is going to shift the vertex down 3 units. So we're going from the origin over to a vertex now of negative 2, negative 3. And that's the only transformations. Other than that, it's going to look like the basic parent function, opening upward with no stretches or shrinks. And we could do a little more detail to find the x-intercepts and stuff, but for now, that's what the graph would do. Okay, so one more thing with part B, and actually part A, these are in what's called general form, or in vertex form is what they're commonly called. And the reason why is that you are able to, just by looking at, like think about part B, for example, just by looking at these transformations and knowing how those work, you can kind of figure out what the vertex is going to be just by looking at it. So it can be helpful to have things in that form. Okay, so that's called standard form again, or I always call it vertex form. Some books just use vertex form. And the reason why, again, is because it's so easy to see the vertex. When you're in this form, the vertex just ends up being whatever the h, the horizontal, and the k, the vertical shift are. That's going to be the vertex. Okay, the a value here is what's going to determine which way the graph opens. Okay, just like before, if you multiply by a negative, it's going to open downward. If it's positive, you will open upwards. But the a value will also give you the vertical stretching. Okay, if it's a value bigger than 1, the graph will be vertically stretched, and so on. So let's see, how can we convert to standard or vertex form? Okay, so this one is in what's called a general form, which is just y equals ax squared plus bx plus c. And that's the form you might remember. That's what you need it in if you're going to solve like using the quadratic formula or even factoring if you're trying to find zeros, okay, or x-intercepts. But to make a graph, if you look at the way this example is written, it's not really clear where the vertex is. Okay, so the way to get it in the form we want, which again, I'm probably going to say vertex form, but again, standard form means the same thing. That's the one again that looks like y equals a times x minus h squared plus k. So we want to take our example and we want to turn it into vertex, or what's known as standard form. Okay, and to do that, it's going to use this algebraic technique of completing the square. So let's walk through how that works. So the original equation is x squared minus 6x. Okay, and what we want to do is we want to do what's called completing the square. So the way that works is we are going to add something here, okay, in order to make the quadratic become a perfect square trinomial. And the trick to doing this is we're looking at, if you think about general form over there, we're going to be looking at this b value and seeing how we can find the c value. So the b value in our problem is -6. So the trick is we're going to take half of that, which is -3, and then square it. Okay, so half of -6 is -3. -3 squared is a positive 9. So that's what's going to go there. But we can't just throw a +9 into one side of an equation. We need to balance it out. So there's two options. We could either put a +9 over here, which would balance it out. But remember, we want to end up looking like this. So I really want this side to just stay as y. So instead of adding 9 on the left side, I'm just going to -9 over here. And you might be thinking, why are we doing that? The reason is this. I'm now going to try and look at this thing as a perfect square trinomial, and I'm going to factor it. Okay, so if you remember about factoring, we need to find two factors of 9 that are going to add up to -6. And when you do it with this process, with completing the square, it's always going to be half of that b value. Okay, so what I mean, it's going to be x minus 3 and x minus 3. Okay, also known as x minus 3 squared. Okay, so remember with the factoring, the one step I didn't show, this would factor, and you can show this step if it helps, x minus 3 times x minus 3. Okay, because the -3 times -3 equals the 9, and the -3 minus 3 more is going to be the -6. And since there are two factors of x minus 3, that's why we are allowed to write it as x minus 3 all squared. Okay, so our final answer in vertex, or the standard form, would be this. Okay, and what that allows us to do, say, what's the point? It now allows me to just visually look at the vertex and think about transformations. It's going to be shifted to the right 3 because that -3 inside, and then down 9. Okay, so given this form, we know a lot more about the graph than we did originally the way it looked up here. We had no clue what the vertex was, x squared minus 6x. Okay, so sometimes you got to do some conversions, and completing the square is the method on that. Okay, let's look at another one. Let's describe this graph, 2x squared plus 8x plus 7, and let's see if we can find the vertex. So again, right now it is written in general form. We want to convert it to vertex form again, or standard form. So let's take a look here. Let's see what we can do. This one has a little bit, another additional step to it. Okay, since the a value is 2, we need to factor that out ahead of time. Okay, and what we want to do, factor the 2 out, x squared, that's going to make this 8x become 4x. And the other trick that sometimes makes this a lot easier is to leave that plus 7 out there. Just leave it alone for now. Don't factor the 2 out of it. Okay, because what we're going to do, we're going to complete the square inside the parenthesis like we just did before, and I'm going to balance it out after the 7 there. Okay, so what I want to do to complete the square again, I'm looking at this b value right here. Okay, after the a value's been factored out, I'm not using 8, I'm using 4. Okay, and 4, do the same process. Cut it in half to get 2, and you square that to get a plus 4. Okay, here's the thing now. We really added a plus 4 there, but remember it's going to get multiplied by that 2. So we really kind of have a plus 8 that we just created here. So to balance out a plus 8, we need to do a minus 8 out here. Okay, it's on the same side of the equation, so I need to do a minus 8 to balance out that plus 8 that we just created. Okay, and now the hard work is basically done. All we're going to do now is that 2 is still there. Let's think about how does this factor. This better be a perfect square trinomial. Okay, and it is. It's x plus 2 times x plus 2. And by combining the terms on the outside, we have a positive 7 minus 8. Those combine to be a minus 1. This is now standard form, or vertex form, and it allows us to identify the vertex clearly. Again, inside inverse, so negative 2, negative 1 would be the vertex of this function. Okay, and here's just kind of a graphical view of it. You can see right over here the vertex would be at negative 2, negative 1, like we said. Okay, and we were able to find that using vertex form. All right, so finding minimum and maximum values. Okay, there's a little process we can do to find the coordinates of the vertex algebraically. Okay, let's say we're not using a calculator to graphing utility. Here's an example. Okay, so the flight of a baseball is given by the function f of x equals negative 0.0032 x squared plus x plus 3, where f of x is the height, okay, and x is the horizontal distance from home plate. So what is the maximum height? Okay, so let's get a little visual going. So this thing, okay, this is going to be height is the y value, and then horizontal distance here. Okay, sometimes that would be called displacement if you're doing a physics type thing, right? Oops, sorry, it's a little sloppy, but horizontal distance. And just a real rough sketch of this thing, it's a parabola. It has a negative a value, so I know it's going to open down and do something like this, right? Okay. Okay, I also know the y-intercept would be 3, whatever the c value is, because that's what the y value would be with if both x's were 0. All right, but anyways, we're looking for the maximum height. So I want to end up finding the coordinates right here. Okay, so there's a little trick. There's not a trick. There's a formula that will give you two things. Okay, the axis of symmetry, which cuts right through the middle here of the graph. Okay, and its x value is going to be the x value of the vertex. Okay, so the formula for that, the axis of symmetry, is always x equals opposite of b over 2a. Okay, and that should kind of look familiar to something. Just on a little side note here, if you think about it, remember the quadratic formula? So what we're going to do, we're going to try and find the axis of symmetry here. Okay, we know the equation of the function is negative 0.0032 x squared plus x plus 1. Okay, so what that's telling us, this is a time where the general form is going to be useful because we need to know what b and what a are. Okay, so again, here's a, and there's a 1 for our b value. So the axis of symmetry, the x value, is just going to equal the opposite of the b value over 2 times the a value. Okay, so negative 1 over, and I'm just doing this on the calculator right now, 2 times negative 0.0032. I'm being careful, I put parentheses around the denominator. Okay, and that's giving me an answer of 156.25. Okay, what that is that is the x value of the vertex. Okay, that is the horizontal distance. Our question now was really, though, what is the maximum height? Okay, so for our vertex, again, we know the x value is 156.25. Okay, how will we find the y value? Well, if we know the x value, right, we know the equation of the graph is right here, I can just plug in the x value that they gave, that we just found, I mean. So negative 0.0032 times that 156.25 squared plus the 156.25 plus 3 Okay, so I just plugged that all in. I plugged the x in, and you can verify in a calculator, and I ended up getting a value of 81.125. Okay, and that y value, okay, that's the y value of the vertex, and the vertex is the maximum, so that would be the maximum height of the baseball. Okay, another way, of course, is to graph it and use your calculator to find the maximum, okay, or graph it in decimals. But sometimes you just have to algebraically know how to find these things as well. Quadratic formula was x equals negative b plus or minus the square root of b squared minus 4ac, right, all over 2a. And if you take a look at this piece of it right here, okay, that actually gives you the axis of symmetry. Okay, so if you think about like a graph, let's say the parabola, I don't know, this one looked like that. So the negative b over 2a is going to give you this part of it. And then what the other part of the quadratic formula is doing, when you're doing this plus or minus square root, it's telling you basically where the zeros are going to be. So it's kind of giving you like that distance. It's how much you need to add and subtract to get to the zeros from the axis of symmetry, which is again x equals negative b over 2a. Okay, but anyways, it's just a side note. So if you remember the quadratic formula, you can kind of remember this part of it. Okay, or if you remember this part of it, it can help you get the quadratic formula. They definitely go together. Okay, but let's get back to our problem. All right, and here's the worked out step just a little bit cleaner. If you want to pause there and take a quick look, it just shows the formula and actually plugging in the numbers. Okay, and one more thing, okay, can we come up with the equation of a parabola if we know the vertex and we know one other point? Okay, so if we know the vertex is at 1, negative 2, okay, 1, negative 2, I'm just going to do a rough sketch here just to have an idea. So 1, negative 2 might be there. And then another point is negative 1, and it's way up high at 14. So let's just say it's like this or something. So this graph, if the vertex is down below that point, needs to be doing something like this. Okay, and we need to come up with the equation. Okay, let's see if we can get this figured out. So we know, again, the standard form or vertex form is y equals the a value times x minus h, remember just any horizontal shift in the vertex, plus k, which is any vertical shift in the vertex. And since we know the vertex, we know h and k. Okay, now the other point just happens to be a random given x and y. Okay, it's not a special point, it's not hk, but it's just some xy that happens to be on the graph. So let's plug everything in, and we should hopefully be able to find the value of a, and then we'll have ourselves an equation. Okay, so the y value, the y coordinate's 14, a is unknown. Okay, the x is negative 1 minus h, which is 1 squared, plus k, so plus negative 2 or minus 2. Okay, so all I did was plug in the h and the k, and I plugged in the x and the y, and now we're going to do some work here and see what happens. Okay, negative 1 minus 1 is negative 2. Okay, negative 2 squared is 4, so this is 4a minus 2. Okay, we can add the 2 to both sides. 16 will equal 4a. And when we divide by 4, we get our value for a. A must equal 4. Okay, so let's plug everything back in. Now remember, vertex or standard form looks like this. A times x minus h squared plus k. All right, so our equation will be y equals the a value we just found is 4, x minus the coordinate of the vertex, and then the y coordinate of the vertex. Okay, and again, just keep in mind, make sure that it seems reasonable. We should have known this part and this part immediately from knowing the vertex. Okay, once you find the a value, that just needs to get substituted in the correct spot, and make sure you just leave y and x as variables because we want this to be the equation of the entire parabola. Okay, so that is some of the things with parabolas, some of the properties that we should be familiar with up to this point.